All right, welcome to MCPS Algebra 2 Final Exam Review. This is Unit 2, Topic 2. I would like for you to have already tried the problems before you watch the video. That'll help you the best. So then you can see, did I get it right? Did I have any issues? And then even after that, try it one more time and you'll probably do really well. All right, so we are supposed to sketch a rough graph of a polynomial function that has each characteristic. So degree is even. Now we know when a degree is even, they have the same end behavior. When a degree is odd, they're going to have opposite end behavior. Here, even, again, they're going to be same end behavior, and odd, they're going to be opposite. Opposite. All right, wonderful. So here, if it's the same and it's a positive, then I know that they're both going to be going up. Both positive, same, and both up. So I could have any type of function. I could have here something like that. That would be even and positive. I could have just a parabola, even positive. You could have any type of function that was both tails ending up. That would give you an even positive. All right, now if I have an odd negative, odd says they're going in opposite direction, and negative says they're going to have a general downward slope. Now how we talked about it, if it was an odd positive, they were like this, but then it really reflected, the negative made it reflect over the x-axis. So if I reflect this over the x-axis, I end up with an odd negative looking something like this. So I could have any type of function that had an odd, so opposite tails and a negative general slope. All right, here it's same because it's even, and negative, if they're the same, then I know they're both going down. So again, we could have anything. We could have a parabola, we could have all sorts of interesting shapes in here, but as long as it's even, same, you wouldn't want to put both. I'm sorry. I'm giving a couple examples. So you would just want to pick one of those and have that be your answer. Okay. So an odd positive means opposite direction, opposite tail ends, and positive is going to have a positive general slope. So we're going to have something like this. Okay. It could have any type of movement in between, but tails need to go in that general direction. All right. So first one, do the functions below have the same end behavior as that when x goes, it gets bigger and bigger negative values? Right, yes, or no? All right. So let's first think about what is our end behavior as we go to the left for this function. So it's even degree and positive. So I know it's going to be pointing up as we go to the left. So as x's get more and more negative, we're going to be going up. So I want to see which of these have the same left end behavior, right? This is left end behavior. Okay, so here I have x to the fourth. Really, I don't need to worry about this at all. X to the fourth, same end behavior. It's the same highest degree. So this is, do they have the same? Yes. Great. All right, x cubed. Now x cubed is a positive, so it has a positive, and it's odd, so it's opposite. So do these end behaviors match? All I care about is the left, and the answer is no. Here we're going to be going down as we go left. All right. Here, 2 to the x. Now that's an exponential function, and it goes like this, and it has an asymptote at 0. So as I go left, I'm actually approaching the asymptote. I'm approaching 0. We're not going up for forever. So this is going to be no. They do not have the same end behavior. All right. Then it asks, do the functions below have the same end behavior as x cubed? So as we go to the right, so the right end behavior, and we're looking at x cubed. So x cubed, cubic, it's odd function. So my end behavior is at positive slope, positive general trend, and it looks like that. So let's compare these guys. again, I don't need to worry about any of that. All I need to worry about is x cubed. Well, if it's x cubed and x cubed, they're going to have the same in behavior. So yes, they have the same. Here, negative x to the fourth. So x to the fourth, even power, so same, and they're both going down. So down, down. As I go to the left, here we're going up, here we're going down. So this one has different. So no, they are not the same. And a logarithm has an asymptote and a function like that. So here we're going up to infinity, here we're going up to infinity really slowly, but we are actually going up to infinity. So that would also be yes. All right, let us move on. So here we're supposed to classify each function by the graph as even, odd, or neither. So in order for it to be odd, we talked in class about how if this point xy is on the graph, then the point, if it's odd, the point is also that's going to be on the graph is opposite x, opposite y. And it has to be symmetric about the origin. So there's this rotational symmetry. If I rotate it this way, 180 degrees, I'll match up to that side. So we want to check that one. If it's even, in order for it to be even, the point x, y, and the point negative x, y also has to be on that graph. So we can check that. And this also looks like it might be even. So let's check x, y, and also the opposite of x, y, right? So this is reflected over the y-axis, so the x's would be opposite. So let's check this one while we're here. So here, it looks like this point is like 1.5, 2, negative 1.5, 2. So 1.52 and negative 1.52. They are both on that graph, so I feel like, yes, this is definitely even. We could check a couple more points if we weren't confident with that. Here, let's double check. Here, this is an easy point, so 0, 0 and negative 4, 0. Those are definitely not opposite x. So I notice if I folded it on this line, the y, then it wouldn't match up. So this is going to be neither even or odd. All right, over here, let's check a point. Let's see, I can't quite see the pointage. I think that looks like 1, 2, 3, 4, 5, 6. Negative 6, maybe 2, negative 6. So the other point would be a positive 2, negative 2 and a positive 6. So let's check negative 2, positive 6. Oh, yeah, it looks like that also is on it. So I feel like this is confident, I'm confident that this is an odd function. All right, so similarly with what I was saying up here, in order for it to be even, this has to be true. In order for it to be odd, this has to be true. We can look at these values, these point values, and say, well, if the point 3, 8 is on a graph of an even function, what are the coordinates of another point? Well, the opposite of the x and the same y, because it reflects over the y-axis, which makes a positive 3 into a negative 3 with the same y height. The graph of an even function has what symmetry? Symmetry about the line. Oh, I don't know why I'm saying the line. About the y-axis. Sorry about that. All right, it's symmetric about the y-axis. All right. So if the point 5, 7 is on the graph of an odd function, then what are the coordinates of the other point? Well, it's going to be the opposite of 5 and the opposite of 7. Now I say opposite instead of negative, because if it started out as negative, it's going to become positive, right? It's just the opposite of whatever we saw. All right, the graph of an odd function has what type of symmetry? It's symmetric about the origin. All right, wonderful. So we're going to look at this graph and evaluate some things. If you haven't already done it, pause the video real quick and try it. All right, so let's read the question. It says, look at the graph of the polynomial function. F of x equals negative x times the quantity x plus 3 squared. what is the degree of f of x? So I noticed this graph and I see it doesn't have arrows, and I actually know that it keeps going. So I'm going to add some arrows on there. I noticed at -3, it bounced off the x-axis. At -3, it bounced off. That makes sense. And then at 0, it went straight through. It has a negative leading coefficient, and it's x to the 3rd power, so it's opposite end behavior. Okay, so what is the degree of f? Now I have x and x squared, so in total I have x cubed. What is the degree? Oops, sorry. Because it's x cubed, I would say the degree is 3. All right. Here it says, as x goes right, as x gets larger and larger, as x increases, our y values, as x increases, our y values are definitely decreasing. They're going to negative infinity. All right, it says write the zeros and their multiplicities. So one of the zeros is x equals 0, and the multiplicity 1. Usually you don't have to write multiplicity 1, but only if it's multiplicity 2. But okay, and x equals -3, and that's multiplicity 2. Okay, multiplicity 1 and multiplicity 2. Give the coordinates of the point where a relative maximum occurs. Okay, so here I'm looking, the max, some people want to give this point because it's like a maximum value. Thanks. Oh, he's not here today. But this right here is actually the relative max. In this general vicinity, we have a peak right here. So at -1, 4. -1, 4 is our relative maximum. All right, give coordinates to the point where the relative minimum occurs. So this, where it's a valley, is our relative minimum at -3, 0. All right, then it asks, on what interval or intervals is the function increasing? Well, we want to always read from left to right. Well, it's decreasing first, and then it stops, and then it's increasing, and then it stops, and then it's decreasing. Now, the county and I disagree a little bit. They say that at this point right here, the turning point, that it's okay to say that it's increasing at that point. I say it stops at that point, but either way, you have to go with what your teacher says. So we only use x values from when x is -3 until when x is -1, right? So on this interval right here, so depending on your teacher, you might say from -3 to -1, not including those points, or you might say from -3 to -1, including those points. I guess it's also possible that you would say x values between -1 and -3, or x values between -1 and -3, including. My personal opinion is that it doesn't include, but I guess maybe it's debatable. All right, so these answers would go here. All right, wonderful. All right, now we need to look at this graph. All right, let's check this out. Look at the graph of this function below. Again, I know that it continues here and here. It asks what is the degree, so I'm going to look up here and I'm going to say that's x squared and that's x squared. I could write it out actually as 4 separate factors, x plus 1, x plus 1, x minus 3, x minus 3. So really there are 4 factors and it's x to the 4th. And I see it's a positive value, so I know it's a positive x to the 4th. So what is the degree? 4. All right, as we go to the left, as we get more and more negative, what happens to the y? It goes more and more positive, so we're increasing. Write the zeros and their multiplicity. We have 2 zeros at x equals -1 and at x equals 3, and they're both multiplicity 2. Uh-oh, I didn't leave enough room. Okay, multiplicity 2, and at x equals 3, multiplicity 2. Great. Give the coordinates of the point where the relative maximum occurs. So here we have a min, max, min. Now it's not the actual max, absolute max, it's the relative max, because these keep going up. But in this general vicinity, that's the highest we get. So 1, 14, 15, 16. 116 would be the relative max. give the coordinates of the points where the relative min occurs. And those just happen to be our zeros. So at -1, 0, and at 3, 0. It's not always the case, but it happened to be in that case. All right, on what interval is the function decreasing? So it looks like we're going to decrease 2 times. I'm going to use a highlighter to help us see that. So let's see. First, we start by decreasing, and then we stop. And then we increase, then we decrease again, and then we increase. So we have to only be talking about our x values. So here, from -infinity to -1, we are decreasing. And then we start increasing, then we stop at 1, we start decreasing again until we get to 3. So I like to write this along the x-axis to remind myself that I'm only using the x value numbers. I'm not going down, I'm going down, but I don't want to use these values. Okay, so on these two intervals, so we would put a little and symbol in there. So on the interval -infinity until -1, and on the interval 1 to 3. All right. All right. Here's some fun problems. So a graph of a polynomial function, f of x, with leading coefficient -2 is shown below. So leading coefficient, we know that -2 is going to start off our equation. All right, so we know it's negative, and we know it has a stretch, a vertical stretch of a factor of 2. We also know some of the zeros. We know this 0 and that 0. We know that at this 0, it only happens once. So x only occurs one time, and it's just x plus 0. There's no plus or minus there, it's just x. So here, if it's -2 is our 0, then our factor is x plus 2. Now, because it bounces off there, I know that it has a multiplicity 2. And that's that. Now, I could check a point. I think that's a really good idea. Maybe -1, 2. -1, 2 looks like it's on our graph. So let's double check. If I plug in a -1, -2 times -1, -1 plus 2 squared. -1 plus 2 is 1. Squared is 1. -2 times -1 is a positive 2. 2 times 1 is 2. So f of -1 is 2. F of -1 is 2. So it looks like our equation matches this graph. Wonderful. All right. So our equation would be -2x times x plus 2 squared. All right. Wonderful. Here's another one. So the graph of a polynomial function, g of x with leading coefficient 1/2. So here's our g of x. And we know the leading coefficient is positive. I see tails pointing up, up. So I know it's going to be an even degree. I see a 0, and a double 0. All right. So here, x minus 1, I'm going to have x plus 1. Here I'm just going to have x. And I know it's only going through one time. All right. Here, it's a double. So I have x minus 2, but it's a double. All right. So if we wanted to write the equation, we'd have x times x plus 1 times x, the quantity x minus 2 squared. And I feel like that would be an accurate equation. Now, is there a value I can check? I could check 2. At 2, we should get 0. Well, that's a pretty simple one. Maybe, is there another one we could check? I'm not sure if this is a point, but I feel like 1, 1 is potentially a point. Let's try that. Okay, let's try it. So, if I plug in g of 1, I get 1/2 times 1 times 1 plus 1, which is 2, times 1 minus 2, which would be a -1 squared. So -1 squared is 1 times 2 times 1 times 1/2. 1 times 1 is 1, 2 times 1/2 is 1, so we get g of 1 is 1. So I feel like we've kind of checked to make sure that our equation is correct, and we know with confidence that this is our equation. X plus 1 and x minus 2 with a multiplicity 2. Wonderful. All right. Now it's asking, let f be that and g be that, h be that. we want to write f plus g of x as a polynomial in standard form. So this just says, this doesn't say times another x. This is f of x, this is g of x, this is f plus g of x. It's just the way we write the notation um, in function notation. So if I need to add f and g together, I'm going to add the like parts, x squared plus 2x minus 7, and I'm going to add up anything that's alike, and I'm going to put it right below it. 2x squared matches this in my g function, and plus 9 matches that. So I'm going to add those two together and get positive 2, positive 2x, oops, and 2 plus 1 is 3, 3x squared. All right, so our f plus g of x function is 3x squared plus 2x plus 2. That would be our answer. All right, if we have to do f minus g, we're going to be really careful. We're going to set it up the same way, but we're going to subtract x squared plus 2x minus 7. But now we're going to take away 2x squared, and we're going to take away 9. So really kind of what I did is I distributed the negative into both of those. Yeah. So I subtract that and subtract that. Now we can add straight down. So here I get a negative 16 and 2x, and here a negative x squared. So f of x, I'm just going to write it here, f minus g of x equals that. All right, what is the degree of the product? If I multiplied f times g, so if I have something that's x squared and I multiply it times 2x squared, my degree is going to be, well, my leading coefficient is going to be 2. My leading term is going to be 2x to the fourth. My degree is going to be 4. It says if we multiply g and h. So if I had x squared, times x, then we're going to end up with x cubed. So if I took 2x squared and I multiplied it times 5x, I'm going to end up with 10x cubed. And really all I'm worried about is the degree. I'm only looking at the very largest term in that. That's how I can figure it out quickly, efficiently. All right, then what happens if I multiply f times g? It says to actually multiply it out. So what is f and h? So we're going to multiply f and h. Let me take a picture real quick. Oops. Here we go. All right, so we are going to multiply these two together. We're going to take f of x, and we're going to multiply it to h of x. That's all that is asking right there. We don't have to put another x in there. So we're going to take our f. I'm going to do the area model for this one. X squared plus 2x minus 7. And then over here we have 5x plus 3. So if I use the area model, I can multiply each individually. 5x cubed. Here we get 10x squared. Here we get negative 35x. So I'm multiplying this times this. And then here we get 3x squared. Here we get 6x. And here we get negative 21. All right. So then you are going to add up like terms, and my like terms tend to make this diagonal pattern. So in total we have 5x cubed, we have 10 plus 3, so we have 13x squareds. We have, let's see, negative 29 x's and negative 21. So f times h of x would equal that. All right. All right, I think we have 2 or 3 more questions. Okay, so here we have Jillian divides this polynomial by this factor, x minus 9, and she gets the quotient, x squared plus x plus 16, with a remainder of 145. Okay, so we want to know, is x minus 9 a factor of that? And they're saying a complete factor. And justify your answer. So in order for this to be a factor of that, we would need to have a remainder of 0. And because we don't have a remainder of 0, so is that a factor? We're going to say no. Because, all right, the answer is no, because we have that remainder. Because in order for it to be a factor, the remainder would have to be 0. No, because there is a remainder other than 0. All right, and then it asks, well, if this is our function, what is the value of f of 9? And we learned about the remainder theorem. The remainder theorem says that if we plug in a positive 9 into our function, we end up just getting the remainder. So the answer should be 145. Now, I feel like I was tutoring a student and we actually tried it to prove it, and it actually didn't come out correctly. So, if you take 9 cubed minus 8 times 9 squared minus 7 times 9 plus 1, I think you actually don't get 145. The answer key says you should get that. So I feel like there is an error in this problem somewhere. I'm not sure exactly where. I haven't worked that out. But the concept is that if you plug that back in, you should get 145. And you may hear corrections from your teachers about the problem. Okay. Let's look at this. Look at the long division below. If p of x is that, so that's this right here. And what is p of 8? So p of 8, we get our remainder, right? You could just plug in 8, 8, 8, 8, but you'd see you end up getting 0. P of 8 equals 0. What is the x-intercept of the graph of that? Well, we know that it crosses at 8. At x equals 8. That is a 0 because we got a remainder of 0. What is a factor of that? We know that x minus 8 is a factor of that because we got a remainder of 0. And it says write a factorization of that. So based on this, I'm just going to say that this cubic function is that times that. So our divisor times our quotient. X minus 8 times x squared plus x plus 7. All right, thank you so much for watching. I feel like that was the last question. Oh, it wasn't. Is that the last? Okay, this is the last one. All right. So a polynomial function of degree 4 has the following properties. Degree 4 tells me it's going to have the same direction. It's either same both up, up, or it's same both down, down, depending on the leading coefficient. Now I see a negative leading coefficient, and that tells me it's not up, up, it's going to be down, down. So the roots are -3. So at -3, I'm going to put a root, and it's multiplicity 1, so it's going to go straight through. At 1, and that's a multiplicity 1, it goes straight through. And then at 4, there's a multiplicity 2, so it's going to bounce. All right, so I'm just going to write a little b here to remind myself that I am going to bounce when I hit that. Make a rough sketch of the function with these properties. All right, so I am going to start down, go through, and bounce. And that is a general sketch of my function. All right, thank you for watching. Happy studying for the final exam.